Thank you very much. I hope I won't disappoint. So yeah, this is this is the last lecture, um, and yeah, we'll talk about a few connections with the real world. At least that's the idea. So, I mean, I know this set of lectures has been very quite technical and very specific in some way because I mean, this is all about the structure of topological recursion and so on, where it comes from, how it relates to Virasol constraints and other formulations. So it's all kind of fairly technical. And if you don't know about topological recursion or don't know why you should care about topological recursion in the first place, then certainly I haven't really motivated this at all. So because the goal of my lectures was really to give a set of lectures so that people can understand what it is, so that when you encounter it in your research, you kind of have an idea of what's going on. But if you've never encountered it, then I really did not spend much time motivating the structure. So yeah, so I apologize for that. As I've said in the beginning, we have to make choices when you give lecture series, and this was the choice I made. But now this is the last lecture, so I thought I would give a few applications. But again, I don't really have that much time, so because it's only one lecture, and the problem is that most of these applications would require introducing the context, which in itself would be a lecture series. So yeah, so I decided to follow a little bit what I wrote in these lecture notes available in the archive, but I expand a little bit on a little bit more on this and give two applications. It's not really applications, two connections. One of them is related to enumerative geometry, which we've talked quite a bit about, but we will talk about it in a slightly different way. So there's one particular properties of the correlators constructed by topological recursion, which gives rise to a lot of interesting theorems or results in various contexts in enumerative geometry. So that will be the first part. And the second part, I'll talk a little bit about the connection with what's called quantum curves and WKB analysis. Again, I won't necessarily mention or motivate why this is interesting. I'll go through what the connection is and what's known about it and what's not known about it. And with the hope that when you encounter these, if you study WKB analysis, exact WKB, Borel resummation, resurgence, all these things are very hot topics these days. Then you might be able to connect with topological recursion. Um, so yeah, that's my goal. I should say there are many other connections, as I've said before. So for example, there are mostly conjectural connections between topological recursion and not theory, not invariance in mathematics and topology. These are fascinating. Most of it is conjectural, so it's still very up in the air whether these connections are true. I mean, they're expected to be true, but they're not proved. So that's really cool. There's like connections too with as I mentioned in the beginning, with AGT and gauge theories and constructing Whittaker states or Gayotto states using topological recursion or area structures. Uh, I won't have time to talk about it, but if you pick any of these papers, now you can understand what the construction is about because you understand area structures and topological recursion. So if you're interested in these connections, what I suggest is you look at the lecture notes I posted. So I tried to put as many references in these lecture notes as possible. So it's got like a list of, I don't know how many, but more than 100 references, I think. So you can go through this list and find interesting papers and see what it's about. Okay, so but let's get started with the first part of today's lecture, which is going to be about one very nice application of the global structure of the correlators and topological recursion to enumerative geometry. So I think I was told by Daniel that you had a few lectures already in this set of lecture series on Gromotron theory. So I won't necessarily explain Gromotron theory, but some of what I'll say will probably connect with other lecture series that you've had. Okay, so let me just say first what we've seen. So we've already seen a connection with enumerative geometry, which is a deep connection, which is really core to topological recursion, which is the following statement. So again, if you take a spectral curve, so let S be a spectral curve. Now I'm going to assume that, as we've done before, with only a simple ramification point, and with this we can construct a set of correlators. So omega gn here is a system of correlators. satisfying topological recursion. Now, for simplicity here, let me just, this is really not needed, but suppose that we have only one ramification point. This is really just so I don't have to write too many indices when I write the formula, but it's really not needed. But we'll come back to this. I'll tell you what changes if you have more than one. And then what we've seen is that if you take your omega GNs, your correlators, and you expand them at the ramification point, there is a very nice expansion. And the coefficient, again, I have this double factorial factor that I keep carrying everywhere with me. But the coefficient here can always be written as integrals over the moduli space of curves, where the entry here is some sort of class here. And then you have a bunch of psi classes. And you have this Xi basis. Now I'm using some of the stuff we've seen. So I'm using the fact that the even classes here, the coefficient with even indices vanish. So I'm only writing the odd ones here. So I'm using basically the linear loop equation if you want, specifically here. But this is the general formula you get. And this class, of course, is what changes depending on the structure curve. And this is what defines a cohomological field theory, as we've seen before. And I have only one E1 here because it's basically a one-dimensional cohomological field theory. And this is what changes here. So if you have, maybe I'll just write it here. Note, if you have R ramification points, all simple still, then what happens is that the coFT become R dimensional. So then you would have, you have to sum over, these maps here evaluated at different basis vector for your vector space that is an n-dimensional vector space that forms your cohomological field theory. Okay, so let's forget about cohomological field theory for the moment, but the point is that the coefficient of the expansion here are written in terms of integrals over mgn bar. So that's a very fundamental statement, and this is the root of all the interesting applications of topological recursion. Right? Now, this is, of course, only for simple ramification point. For general ramification point, we expect a similar formula, but this is still conjecture. So the general formula here is not known for the general case. We know some particular cases, but we expect a similar formula in general. And I was looking at some references to some other papers. One thing I should remark again, so there's, as I said, there's a vast literature on the subject right now, but it's still by the way, I mean, there's a vast literature. There's a lot of papers. However, there's not that many good introductory papers. I mean, there's my set of lecture notes. I don't know if it's good, but there's a few other lecture notes that have been published over the years. But the point is that it's still a pretty young research area, so there's no book or anything like that on the topic. So that makes it harder, I guess, to enter into the area, unfortunately. But hopefully these lectures help. One thing I want to mention is that because there's a lot of papers and it's fairly young, there's different notations. There's no like kind of conventional necessarily notation for a lot of these things. So for example, these double factorials that I keep carrying around, often they are, in many papers, they are included in the definition of the Xi basis. So for example, in the formula above, you could replace this by basically the double factorial. So you always have to be careful when you look at the papers. So sometimes it depends how you define the Xi. So the way I've defined them was using the projection to the powers of the local coordinates. So there was no factorial involved, but you could define them with these double factorial, and then you don't have to carry them everywhere. So just a convention. Okay, similarly, there's also something I forgot to mention when I talked about array structures. So the convention I'm using for H bar in these notes and in these lectures is different from the original Kontsevich-Solomon convention. So if you look at the original paper, you'll see that you have to change the formula a little bit. Yeah, that's what happens. Okay, so the point here, the moral of this, so this is a very general formula. This is the core connection to enumerative geometry. And the moral of this formula, you can forget about the cohomological field theory, but the key point is that the coefficients of the expansion of the correlators at a ramification point, and not only that, but also in the C basis, this natural basis of define, are integrals over mgn bar of something, right? So they are basically the correlators of a semi-simple cohomological field theory. Now, this is cool. This is very nice. But it raises a question, because these correlators have more structures than only their local expansions at the ramification point. They are actually symmetric differentials defined globally on the spectral curve. So the question is, what happens if you expand the correlators at different points, right? If you expand the omega gn not at a ramification point, but at another point on the spectral curve. Now, if you expand at a random point, probably there's nothing interesting. I mean, you get some coefficients, but I don't know what they mean. But maybe there are some specific points where these coefficients have a nice interpretation. And if they do, that's pretty cool, because then maybe you can relate the two expansions, right? You see the expansion at the ramification point in the C basis was very special because it was a finite sum in the X's. And the X's are globally defined differentials too. So you can expand the X's at a different point, and that will relate this expansion in Xi to the expansion at a different point. And that might give rise to very interesting relation between the coefficients of the other expansion and the integrals over mgn bar. Right? So that can give rise to some very interesting results. And it turns out that indeed this general idea gives rise to a lot of well-known theorems in other areas and generalization of these theorems to new results that were not known before. Okay, so I'll give you some examples of that. So the first example, I was thinking of maybe doing it in more detail, and then the other ones I'll just point out what happens. Okay, so the first example is the connection with Hurwitz numbers. Have you guys heard about Hurwitz numbers before in these lectures? A little bit, maybe not. Okay, so we'll see. I won't spend too much time defining Hurwitz numbers, but I need to at least tell you what this is about, what this counts. What is this? This is a classical problem in enumerative geometry. So I'll define Hurwitz numbers first and then tell you how it's connected to topological recursion. Okay, so we're going to start with simple Hurwitz numbers, but because that's the simplest case, but a lot of what I'm going to say actually generalizes to all kinds of different Hurwitz numbers. So what are simple Hurwitz numbers? So these are numbers that count something, right? And they count ramified coverings of the form. So you cover P1 by a Riemann surface. So C here is a Riemann surface. So compact, connected, genus G for some G, Riemann surface. And then what you do, so if you just count like this, that's not a well-defined count, but now you have to specify something, impose something on the coverings. And to define the Hurwitz problems, what you do is you prescribe the type of ramification. So if you do single Hurwitz numbers, what you do is you prescribe the ramification type at one point, which we usually set to be infinity, but it could be anywhere, but just conventionally put that in infinity. And then you only allow simple ramification elsewhere. Okay, so I'll do a picture which will probably help. Okay, and then that's not so important, but we count with the weight, which is 1 over the size of G, where G is the automorphism group. Okay, so what does that look like? So basically the point here is you have a covering. So you have your P1 here. Again, this is a cartoon version. You have a covering. There's a special point here, infinity. And then, okay, you could have something like this. You have some sort of ramification at infinity. For example, you could have something like this and something like this. Right? These 2 points, say, are above infinity. So my picture is not very good. Let me do it a little better. Okay, so the 2 points are infinity. Oops. And then you can have simple ramification elsewhere. So I could have simple ramification points things like that, right? So there are other points here anywhere on P1 where two of the sheets meet, but not more than two. Okay, and there's of course a relation here between the degree of the map. So my picture here is a degree 5 covering, so between the degree and the genus and the ramification, and this is the Riemann-Hurwitz formula. So you can relate all of these different things here. Okay, but the point is that the freedom here is in the ramification profile at infinity. So this is what you specify here. And this is specified by a partition. This is indexed by a partition of the degree of the covering. Say degree D. So let's call this partition mu. So in this case, for example, it would be the partition 3, 2, right? There's like 3 sheets meeting at one point and 2 at the other point. Okay, so that's basically, that's the thing. And then you define the Hurwitz numbers here. I'm going to write them like this. So mu is the partition at infinity. So this is the ramification profile at infinity. G here is the genus of the covering of C. And then N here is an extra. You don't actually have to specify it in principle because it's specified already, but this is just for clarity later. So this is just the length of the partition, right? So it's the number of preimages at infinity. Okay, so this is what's called a simple Hurwitz numbers. Simple Hurwitz number. And these are rational numbers that you can calculate in principle. And in fact, many of them have nice formula here, especially for simple Hurwitz numbers. Then there's lots of nice formulas that are known about these numbers. It's a very classical problem. Again, Hurwitz is the first one that studied it, I think. But it's yeah, it's a very interesting problem. So if you're interested in that, by the way, there's a very nice book of Cavalieri, Renzo Cavalieri, and Miles. What's his first name? Eric Miles? I'm not sure. Cavalieri and Miles. They have a textbook that introduces Riemann surfaces and so on, and Hurwitz theory at a level that is very very accessible. So that's very nice. Now, this is simple Hurwitz numbers because we specify the ramification profile at a single point, infinity. Everything else is simply ramified. If you have double ramification, double Hurwitz numbers, you would specify 2 ramification profiles and 1 at 0 and infinity. Triple would be 3 ramification profiles and so on and so forth. Okay, so that's the idea of Hurwitz numbers. Okay, so once you've defined that, then you can construct a generating series for these numbers, right? This would be very natural. So I'm going to write it like this. I'm going to introduce some coordinates, x's, x1 to xn, and I'm going to write a sum. Let's introduce some positive integers, mu1 to mu n. Now I have a factor here, which is not really relevant. Again, it's just to make the statement work later without extra factors. And then I have my Hurwitz numbers here. Now you may notice here I'm summing over all positive integers, while before I had mu was a partition, so it was an ordered set of integers, but you can symmetrize. You can define HGN for any bunch of integers just by symmetrizing. So that's the same thing. And then I'm going to introduce these coordinates here. And usually you don't put differentials here, but now I want to put differentials for a reason that will become clear very soon. Okay, so this is a natural generating series. It's not that different, for example, to the WGN that we talked about last lecture when we talked about the generating series for expectation values of traces. It was expanded in 1 over x. Now it's an x, but it's kind of a similar type of expansion. And the question is, are these related to TR? Topological recursion. This is not obvious at all, right? There's no, these HGNs are not just directly integrals over MGN bar. And also this would not be a XC basis anyway. So this is not the expansion that we get by expanding correlators at ramification points. So that's a very good question. It turns out that they are, of course, otherwise I would not talk about that. So let me tell you how they are related. And this is the toy model of a lot of these applications I said to enumerative geometry. So the spectral curve here is a kind of interesting spectral curve. So let me call it the Hurwitz spectral curve. So what is the spectral curve? So we're going to start with, okay, we still work on over C, but then X, instead of being just a, Z square, as we've done so far, it's now given by Z e to the minus Z. Okay, omega 0, 1, the one form is now 1 minus Z dZ, and I will take the standard canonical or fundamental bidifferential. Oops, sorry, not X, but Z. Okay, so that's the usual one. Okay, so now this function is not, doesn't come out of nowhere. If you know about this, you will know that Z here is related to the, it's called the Lambert W function, which appears in graph theory, like counting some sort of graphs, and also appears in the context of Hurwitz theory. This was already known. So that's, it's not completely unreasonable that this will be related to Hurwitz theory. Okay, so if you look at this X, you will see that over C, there is actually a single ramification point. It's not at the origin anymore, but it's at Z equals to 1. And so one way to see it, just calculate dx. Look at the 0 of dx, you'll get a single 0 as Z equals to 1. And if you look at the local behavior, this is Airy type, so it means that it's simply ramified R equals 2, and omega 0, 1 starts with a 0 at Z equals to 1. Okay, great. So now we can apply what we know. So this is an admissible spectral curve, so we can use TR. It calculates a bunch of differentials, and then you can expand at the ramification point. So this is the standard expansion that we know. Again, if we do that, in this case, what do we get? So now we know we get integrals over mgn bar. Now if you follow the procedure from the DOS paper, for example, where they related these correlators to cohomological field theory, you'll get that here you have a very particular class. This is what is the cohomological field theory here, and you have your bunch of psi classes and your C basis as usual. Now I'm again only writing the odd ones here for simplicity. Okay, so this would be this is what you get, just applying the procedure from the DOS paper or some other papers since then to get the expression, the expression for the coefficients in terms of integrals of moduli space of curves. These are called Hodge integrals, by the way. So this class that I wrote here is if you have a course on Riemann surfaces or MGN bar or Grommelton theory, you will certainly see this class appearing quite a bit. There's another bundle you can construct on the moduli space of curves, which is called the Hodge bundle. So I'm just going to tell you what it is, but I won't tell you what the bundle actually is. But again, you may have seen that in your lectures on Grommelton theory. So this is the Hodge bundle on the moduli space of curves. The lambda classes are the Chern classes of this bundle. And then this class that I just wrote, if you put a T here, would be basically the sum of those, the Chern character, right? Is that how it's called? And then you set T equals to 1, and you get what I have there. Okay, and then for, of course, a particular value of K's, there's only one of these terms which will be non-zero. It has to match with the dimension of the moduli space, so this will pick the right lambda classes here that appear. Okay, so again, this is not so important. Oh, I'm supposed to update my tablet. Let's update later. Okay, so it's not so important what it is here, but this is what you get from standard procedure in topological recursion. Great. So that's the coefficient you get. Now, question is, if you take that spectral curve, what happens if you expand at other points, as I said? So in particular, there's a special point here, which is the puncture, as we say. So if you expand in each variable at the point where this is 0. Okay, so why is this the puncture? Well, this is really, you send xi to go to infinity. So, which is, of course, not included in my spectral curve. This is the puncture at infinity, because in my spectral curve here, I take the Riemann surface to be C, but at infinity, there's an exponential singularity here. There's an essential singularity at infinity, so that's why we don't include it here. But but you can expand near this point, right? You're just expanding near the point, so that's perfectly fine. What are we going to get? Well, it turns out that you can actually do it here very explicitly. And this is always the case because, as I've said, the key, and this is one of the key results, is that you have, when you expand at the ramification point, you actually have a finite expansion in the Xi basis. And the X's are globally defined differentials, globally defined one forms. So you can expand the X's at different points, right? And in this case, if you do it, so again, this is just technical formula, but I just want to show you how it is so that it doesn't look too mysterious. If you expand these X's, what you're going to get, if I'm not mistaken, so I looked back at the paper, so hopefully I didn't make a mistake when I transcribe, because again, there's a number of different papers and there's different conventions, so I hope I didn't make a mistake. But if you expand X's at the punctures at x equals to 0, you get a series that look like this. Now I'm going to write I think here, just in case I made a mistake. But it's something like this, right? And you can find, so by the way, where this whole story comes from, I should put some reference here. So it was first conjecture in a paper of Marcos Marinho and myself in the very early days, 2007. And really the credit should go mostly to Marcos for this conjecture here. And then it was proved a couple of years later, I think, by Enar, Mulazi, and Safnuk. So these are the first papers that talked about Hurwitz, the connection with Hurwitz theory. And since then, there's been many, many papers that generalize this in all kinds of directions. But okay, so you have this expansion here, so you can plug that in your correlators, and you're going to get a double expansion. So you now have an expansion in the mu's, which are positive integers, and you get your expansion in the k's. So let me put some brackets here. Now you have this crazy looking factor. What was it? Mu I plus 1 plus ki over mu I factorial. You have your integrals over moduli space of curve, psi classes. Your Xi basis is now expanded, so instead you get the x's, x1 mu1 plus 1 to xn mu n minus 1 dx1 dxn. Okay, now what you've done, you've re-expanded the correlators at the puncture. Great, but the cool thing is that this thing in bracket, so the term in bracket here, is actually equal to the Hurwitz numbers. So this is up to this weird factor that I had before. Again, I hope I didn't transcribe things wrong, but I think this factor is there. But basically, you end up with up to this factor, just the Hurwitz number before. So in other words, this expansion at the puncture is precisely this generating series that I introduced here. Magic. Isn't that very cool? Now, this relation between the bracket terms and this is a celebrated formula. This is what's called the ELSV formula. This is a very well-known formula in Hurwitz theories, Hurwitz theory, due to 4 people called ELSV. And I never remember their name, but I think it's Ekedal, Lando, Shapiro, and Weinstein, I think, hopefully. So this is from the 90s, I think. I'm not sure exactly when that formula was published. But the formula is basically saying that you can rewrite Hurwitz numbers as integral over mgn bar, which is a very non-trivial statement. Okay, but this is in some way that's one way to prove. In fact, this is how it was conjectured in my paper with Marcos and proved. Well, this is not the way it was proved, but that's one way to prove that you get Hurwitz numbers. It wasn't proved this way because the whole relation with cohomological field theory wasn't known at the time. But one way to prove it would be to say, well, the omega GNs expanded at ramification points give rise to these integrals with the Hodge classes, the lambda classes appearing, these Hodge integrals, and then you basically use the property of the one form for that particular spectral curve, so you can expand it like this. This is a fairly simple calculation, and then you would use Eli's formula and see that you get Hurwitz numbers. Okay, so that would be one way of doing it. But the really cool thing here is not just, I mean, if all it was here is that you see ELSV formula appearing here, that would be okay. That would be cool. Some way that's a nice interpretation of ELSV formula, which is that it relates two different expansions of the same correlators. That's the interpretation here. But it's not necessarily, it would not be groundbreaking. But the cool thing here is that you can actually prove the ELSV formula in this way, right? So how do you go? So if you expand at a ramification point, you get integrals over mgn bar. That's what I just said. And if you expand at a puncture, in this case, infinity, you get Hurwitz numbers. So that's the cool statement. The reinterpretation is that the relation between the two expansions are or is precisely the LSV formula. That's a nice reinterpretation. But the cool thing here is that if, and that's of course an if, no comma here. Oops. If one can prove that, or independently, that TR produces, that TR generates Hurwitz numbers at infinity, then that gives a new proof of ELSV, right? So in other words, you can either use ELSV to show that you get Hurwitz numbers, which is what I just said before, or if you can prove that you get Hurwitz numbers independently, then by relating the two expansions, you've just proved the ELSV formula as a consequence or corollary of topological recursion. And that's pretty cool because this is what's used to find all kinds of generalization of ELSV. But how can you prove independently that you get Hurwitz numbers at infinity? This is actually how it was proved originally by, if I'm not mistaken, by Enal, Mulaz, and Safnook. So what you can use is other things that are known in Hurwitz theories. So for example, in Hurwitz theory, there's something called cut and join equation, which is a kind of differential equation satisfied by generating series of Hurwitz numbers. And through formal manipulations, you can show that the cut and join equation is actually equivalent to topological recursion for the correlators obtained by summing over Hurwitz numbers at infinity. So that's how it was proved, and that's an independent proof that does not use ELSV formula. So that would, using that, then you can prove ELSV formula. You can also, there's like all kinds of fermionic methods that have been developed for Hurwitz theories, and using those you can also get proof topological recursion or some similar results. So the point here is that you either use ELSV formula to show that you get Hurwitz numbers, or if you can do it independently, you get a proof of ELSV through this connection. So I think that's a pretty cool application of the formalism of topological recursion. And the key feature here is the fact that the correlators are globally defined object on the spectral curve. So there was a question here. How does one usually go about determining the spectral curve given a whole bunch of numbers that we know should satisfy TR? So that's a very good question. So if you know they should satisfy TR, then you can get the spectral curve by basically looking at the 0, 1 part of your number, right? Because the spectral curve really, so the omega 0, 1 here is really to, if you expand at, in this case, in X, for example, to get Hurwitz numbers, this should generate the Hurwitz numbers H0, 1. Right, so and if you know omega 0, 1, well, basically, well, I guess it doesn't give you necessarily the full data of the spectral curve, but it gives you a lot about what the spectral curve should be. But you need to know a little more than omega 0, 1. But basically, yeah, so that's a good question. But there's actually some nice, yeah, I don't know what's the easiest way of answering that, but Motoriko Mulazi and Olivia Dumitrescu have a series of papers that's from a while back, maybe 10 years ago, that where they study this question. So they basically talk about how to get spectral curves. I think Motoriko actually published a paper very recently too. And they have a review as well from 3 years ago. So that would be a very good place to look at. So they basically study this question. So if you have some numbers, how do you get the spectral curve in a very nice way? And it's basically, it amounts to looking at 0, 1, but you have to be a little careful with how do you get all the data of the spectral curve. In the case of Hurwitz numbers, the way we did that in that original paper with Marcos was using a limit. So, and this connects to the story I will talk about in 5 minutes. So there's a generalization of what we just talked about here, similar idea where we expand at infinity and get some nice enumerative geometry where we get Gromov invariance of toric-Calabi-Yau threefold, which is basically topological string theory. And in that context, there's a well-known limit for topological string theory on the what's called the resolve conifold. There's a parameter there called the framing parameter. And if you send the framing to infinity, it was already known that you get Hurwitz numbers. And it's fairly easy to see from the Gromov problem that this amounts to calculating Hurwitz numbers. And if you do this limit in the spectral curve, so in the case of Gromov theory, you know what the spectral curve should be because there's mirror symmetry and it's what's called the mirror curve. Anyway, that's a long story. But and then using the limit of that mirror curve, you get exactly that curve that I just wrote down for Hurwitz numbers. This is how we came up with that curve in the first place. But the study of the question you're asking is done much more systematically in Motoriko's papers. So recommend looking at that. Okay, so that's kind of cool. And then you can use this approach and, as I said, look at the same approach in many, many different contexts. So there's many generalization already just in Hurwitz theory. So let me just mention a few. This is not exhaustive by any mean, but if you just look at Hurwitz theory, there's many generalization of Hurwitz numbers. And if you change the spectral curve slightly, you get generating series for all these different cases. So one example is if you do that, introduce a parameter R here. So that looks like an N, but that's meant to be an R. And then you change your omega 0, 1 to be this particular one. So that should be R minus 1. And you keep the same omega 0, 2, which will be the case in all my examples. Okay, and you do the same thing. So here, if you look at the ramification points, you'll get more than one ramification point here, but they're all simple and array type. So that's great. And there's still a puncture at infinity because there's an essential singularity at infinity. So if you expand at infinity here, you'll get what's called R orbifold Hurwitz numbers. So these are just like Hurwitz numbers, but we have some orbifold structure on the base curve and the covering. Okay, so that's kind of cool. And then if you do the same idea, which is that you look at the expression at the ramification point in terms of integrals over mgn bar, and you relate to the expansion at infinity, that gives you a way of writing orbifold Hurwitz numbers in terms of integrals of mgn bar. And it turns out that this was already known. This is called the Johnson-Pandari-Pandey-Tsang formula, which is much more recent than the ELSV formula, but it's basically an orbifold generalization of ELSB. So this was already known. So in some ways, not like a new formula, but it's a new reinterpretation of this formula, which is basically the same idea. But then if you change a little more, so if you just keep the same z and the same x, but change your omega 0, 1, remove the z to the r minus 1. So in other words, you change the variable y, the function y if you want. Then you'll get something that is called R-spin Hurwitz numbers. So this is more complicated to explain. So it's not just an orbifold structure. It's also called completed cycles. So there's no way I could explain that in a few words here. But it's, again, a generalization of the count of ramified coverings of P1. And in this case, you can do the same thing, relate ramification points to infinity. And in this case, it gives rise to a new formula. This is the what's now called RELSV formula. And this was not known, so it was conjecture, I think, if I remember the history, it was conjecture by Zwankin in the past, but wasn't proved until topological recursion was used to prove it. So this was proved in a paper of I have the letters here, DKPS, and I think is Dunin, Barkovsky, Kramer, Popolitov, and Shadrin, I think. Fairly recent, maybe 5 years ago, something like that. 6 or 7 years ago, I don't know. But it's again the same idea. You just relate it to expansions. So just and that gives a proof. And there's many, many more. So this is just wanted to point out these two because that's the first one that is not a known formula that you reinterpret. But you can do many more generalization. There's like some much more systematic. There's some papers that came out a few years ago with much more systematic study of Hurwitz numbers and topological recursion. So John Harnad and collaborators have some, and Rainey Kramer has a few too. So yeah, if you're interested, you can look at that. But the same story is always there. Okay, and one thing I want to point out because I've said at some point that I think I've mentioned that one of the generalization of TR is to Trent's algebraic curve, but I didn't say what it is. So using exponential singularity. So this is one example where you get something very interesting. So if you take the R spin curve, the second example above, where you get R spin intersection number, but you do the very, very small modification, which is that you think of your Riemann surface as P1 and not just C. So you want to include the point at infinity in your Riemann surface, which is actually an exponential, an essential singularity. So at that point, it's not a standard ramification point. If you include it, you have an infinite degree covering, and at that point, all the sheets meet. So it's kind of, you can think of it as an infinite ramification point, where you have an infinite order. But of course, these things are a bit tricky because everything is infinite. So you end up with lots of sums that may be divergent, like infinite sums. But you can, in principle, extend the formalism of topological recursion to include contributions from these points. This is what's called Trent's algebraic curve in the literature. So these are curves where you include these essential singularity, and you get something really cool. You take the exact same curve, but you include contributions from that point, and you get a different type of Hurwitz numbers. Again, you expand at infinity, and you get what's called Atlantis Hurwitz numbers. So these were defined in paper of Shadrin and collaborators, again from a few years ago. And it's kind of an interesting story because in that paper, they mentioned that this is one of the first example of Hurwitz numbers that does not fall within the context of topological recursion, because indeed you could not, if you apply topological recursion naively to that curve, this curve here, you get R-spin Hurwitz numbers, not Atlantis Hurwitz numbers. But what we realized is that actually there are two ways of applying topological recursion. You can either ignore the exponential singularity or include it, and that is what makes the distinction between those, which I think is a really cool story. So this is a paper of mine with Kramer and Weller from a few years ago. So I think that's a very, very neat little story. Okay, but the moral here is that relating different expansions give rise to really fun formula in enumerative geometry. Okay, and then so I want to give you, so I'll give you two more examples of this, but not, I mean, the first one I'll just do very quickly because I want to have time to at least mention the last one. So one interesting example where you get also nice geometry is the story of Gormington theory of P1. So Gormington theory, as you know, is the study of the moduli space of stable maps. So instead of looking at curves, you now look at stable maps from a Riemann surface to a target space, which in this case you would take to be P1. And it turns out that there's a very similar story. You get Hurwitz, no, not Hurwitz, no, Gormington invariance of P1 by looking at a very specific spectral curve. So the spectral curve here is this one. So you take x to be z plus 1 over z. Omega 0, 1 is a bit of a mess, but really what it is just that y is equal to log of z. And you take the same omega 0, 2 as usual. So here there are two ramification points at z equals plus or minus 1. So you have two copies of your constraints if you want. And so let me write this down. And they're both of Airy type, so usual thing. And then if you expand, well, if you expand at ramification points, you'd get as usual some coft. But if you expand at infinity, you get Grommelton invariance, but you get stationary. You basically get stationary Grommelton invariance of P1. So this is a story that was first conjectured by Norbury and Scott, and then proved later. Forget in which paper, actually. Okay, and then the relation between infinity and ramification point is essentially the given-Talbot reconstruction theorem for semi-simple cohomological field theory. So it's kind of a nice story here as well. But the cool thing here is that you get the stationary, you get the full theory if you want, or at least the stationary part of Grommelton theory of P1. And you get that out of two copies of Virasoro constraints, where there are two ramification points. That's basically what topological recursion is. Now, there is also well-known Virasoro constraints from Grommelton theory of P1 due to Okunkov and Pandari-Pende, but these are very different. So this is not the same at all. These their Virasoro constraints are completely different from the ones that you get here for Grommelton theory of P1. So that's kind of a nice, nice little story. Okay, and then if you keep going in Grommelton theory, this is the last example I want to talk about for the enumerative geometry application. So one of the big story that was proposed in the very early days of topological recursion is that you can recover Grommelton theory for any toric Calabi-Yau threefold. So let me call that X. So this is what was known as the remodeling conjecture in the literature. So it was originally proposed in a paper of mine with Clem Marino Pasquetti, and then it was proved by Enal Martin and also Melissa Liu and Boan Fang and Zhenyu Zhong in two papers a few years after. And this is basically the connection between topological recursion and string theory, or topological string theory, if you want. So X here is a it's always non-compact, so it's a toric Calabi-Yau threefold. And Grommelton theory of this is essentially a model topological string theory. So this is a mathematical formulation of a model topological string theory. And the story here is very nice because in this case, the spectral curve has a very natural interpretation because it is the mirror curve. So the story of mirror symmetry, which is completely independent of topological recursion, is that there's a duality between A model topological string theory and B model topological string theory. And in particular, in the case of toric Calabi-Yau threefold, this has been studied a lot. So here you have a toric Calabi-Yau threefold. On the mirror side, you'll get another Calabi-Yau threefold, which turns out to be a conic bundle. So let me write it very schematically. It looks like this over C square, C star square. So here X and Y are C star variables, U and V are C variables, complex variables, and P is some polynomial here, which is basically determined in terms of the toric data. So the cool thing with toric geometry is that the manifold is completely specified combinatorially by what's called the toric data or some graph or something like that. And so that makes it very easy to study. That's why toric geometry has become so popular. And you can get the mirror directly. This was studied by Oli and Vafa many years ago. So you get the mirror directly, and then the B model on that mirror should be dual to the A model on the toric or Grommelton theory of the toric Calabi-Yau threefold. And you get the mirror curve directly. So the mirror, what's called the mirror curve, which will become the spectral curve for us, is the degeneration locus of this fibration. So this is a conic fibration, right? For any point in any values of X and Y, you get a conic, UV equals something, right? But it degenerates to two lines when the right-hand side is 0, right? So the mirror curve here is this part of the curve, which is the degeneration locus of the conic fibration. And this turns out to be the spectral curve of the problem. Okay, so in other words, one way to think about it is that topological recursion provides a formulation of what the mirror model should be. So the B model is notably difficult to formulate mathematically. A model is really just going within theory if you want, but B model is much more complicated to formulate, even though it's a simpler physical theory. And you could think of topological recursion as being a formulation of the B model. And that's the story that we proposed many years ago. And for example, just an example, this is what's called a toric diagram for local P2, which is the total space of the canonical the bundle O minus 3 over P2. And the mirror curve here, one way to think of the mirror curve is that you can just fatten your toric diagram here, and that gives the mirror curve. So the mirror curve here would be, of course, it's given by a polynomial and the variables x and y, but the topology or the geometry of the curve is that it's a genus 1 curve here, and it has 3 punctures because x and y are C star variables. So there's some points missing here. Okay, so there's that's a long story. So I just have a few minutes here, so I can't delve into the details here. But the idea of that story is very similar to the Hurwitz cases. So again, you have a mirror curve, which plays the role of your spectral curve. And the cool thing is that the mirror curve only has, this is always true, only has simple ramification points of every type. So you can just apply topological recursion as usual. And if you expand at the ramification point, it'll give you some co-ft, which in this case, you'll get some Hodge integrals. So integrals over mg bar with these Hodge classes. These are called triple Hodge integrals, what you'll get here generally. And if you expand at the punctures, so in this case, there's more than just one punctures at infinity because there's a few points missing in the curve. But if you expand there, then you'll get Grommelton theory. More specifically, the correlators would give you what's called open Grommelton theory of the toric space. So this is now a generalization of Grommelton theory where you look at maps from open Riemann surfaces, so Riemann surfaces with boundaries. And then in this case, you'll get that the boundaries have to map to a Lagrangian some manifold of X, which is what's called the eigenegic Bava branes of your toric manifold. But anyway, these are all details, and the free energies, the FGs, actually give closed Grommelton theory of your target space. And the cool thing is that, again, you can relate these two. What do you get? You get an expression for Grommelton invariance in terms of integrals over much less space of curves. And what you get here is a mirror statement to localization formula in Grommelton theory. So it turns out that in Grommelton theory of toric threefold, you do have a way of rewriting Grommelton invariance in terms of integral over mgn bar. And the idea is simple. So let's take the Grommelton theory of local P2 again. Turns out that there's a torus action. These are toric manifolds. So there's an actual torus action, which also become a torus action on the modular space, stable maps. And it turns out that these integrals localize over the torus fixed points, which corresponds to the vertices of the toric diagram here. So these are the torus fixed points. So Grommelton theory localizes to these fixed points. And in fact, what you end up with is some integrals over mgn bar of some sort, which arise from localization of the integral over the moduli space of maps to the torus fixed points. But the mirror statement is exactly this relation that I've been talking about, because now you fatten the mirror curve, you fatten the toric diagram to get the mirror curve, something like that. And it turns out that the vertices of the toric diagram here are mapped to the ramification points. So these are the ramification points of the curve. So in this case, the curve mirrored to local P2 has 3 ramification points, genus 1 curve with 3 ramification points. And so you can think of TR as localized, if you want, to the ramification point, right? What it does, TR, you can expand the correlators at ramification points, and you do get, again, integrals over mgn bar. So this is really a mirror statement. And this localization, by the way, here is also, sorry, this is basically essentially what's called the topological vertex, which you may have heard of in other lectures. This is the localization on the Grommelton side, but what we're talking about here is a very similar localization, which is what TR does on the B model side, on the mirror side. So this is very cool. And this is essentially the idea behind the proof of this remodeling conjecture in both papers of Enumerative and also Melissa and friends. I mean, it's very, very complicated proofs, but essentially the idea is to reduce both sides to sum over graphs. So you can do that using localization in Grommelton theory. You can rewrite calculation of Gromit invariance in terms of sum over graphs. The other side, you can do the same thing with topological recursion. This is the graphical interpretation I talked about. You can think of these graphs as the composition of Riemann surfaces as graphs. And then you compare the graphs and compare the weights, and you basically show that the sums are the same. So that's essentially the proof. But fundamentally, it's just saying that TR produces a mirror statement to localization of Gromit theory. I think that's kind of cool. So the moral here, I guess, the upshot of this discussion is, maybe I'll write it because that's important. The upshot of this whole discussion here is that, well, first, the global structure of the spectral curve is cool. So it plays an important role. And the point here is that if you know, basically relating, that's something that whenever you have topological recursion appearing somewhere, you may want to do that and see what happens. If you can relate the expansions at different points, so in particular expansions at ramification point and expansions at punctures, when you have punctures, then it often leads to very interesting results. And of course, depending on the context, these results might take different forms. Like it's either ELSV, JPT, localization, whatever. But abstractly, in the context of topological recursion, it's always the same idea. And this shows the power, again, of doing things abstractly, right? Whenever we study things about topological recursion itself, it can have consequences in many different areas, right? And it may lead to some very interesting results in these different areas. Okay, so anyway, this is what I want to talk about from the point of view of enumerative geometry. So maybe it's a good time to take a break, and then we can talk about quantum curves for the second part of today's lecture. Okay, so yeah, let's talk about a second application. So we've talked about enumerative geometry. Well, application is not the right word, but another connection with other areas of research. So what I wanted to talk about briefly in this second part of the lecture is on quantum curves, because that's a very popular topic these days, or rather WKB analysis and non-perturbative analysis is very popular. So yeah, so maybe I'll talk about that for the second part, and we'll see how far we can go. So what is the idea of quantum curves? So what is the idea of the story in the first place? So the idea here is that from the very early days of topological recursion, it was thought that TR should somehow provide a quantization of the spectral curve. Now, or rather a procedure for quantizing the spectral curve. Now, the root of this statement is quite deep. Now, it comes from matrix models, but you can also think of it in terms of integrable systems and integrability. And this is something that's beyond what I can say in this lecture and also beyond what I understand. But in the context of matrix models, the intuition is actually fairly simple. So this was probably the original paper that talked about this is a paper of Berger and Hénard, 2007 probably, or 2006. And the intuition here in matrix model comes from a very simple fact. So the intuition comes from matrix model, and the very simple fact that is used in matrix models is the following statement. I mean, essentially, the statement that's used is a formula that you probably all know, which is that the determinant of the matrix of a matrix A is equal to the exponential of the trace of the log of the matrix. Where, of course, exponential and log here are just thought of as series for matrices. Okay, so that's a very, very well-known relation. But the point here is that when you study matrix models, there's two types of observables really that are well, at least that there are two types of observables that are interesting. There's one which is these product of traces, which is what we talked about before, because these are going to be invariant under these diagonalization of the matrices. And there's also the determinant of the matrix, which is an interesting observable. And product of traces give rise to the correlators of your matrix model. The expectation of determinant will connect with what I'll call the wave function here. So the point here is that this gives a relation between an observable, which will become the wave function, and basically the exponential of a sum of product of traces, which is determined in terms of correlators, basically topological recursion. Okay, so that gives rise to a construction of an object called the wave function. And then this object satisfies all kinds of properties in matrix models. Is all called determinant of formula. And in particular, it gives rise to the quantum curve correspondence that I'll talk about here. Okay, so this is, of course, beyond what I'm saying here. I'm not going to give you the whole context in matrix models, but I want to just explain that this correspondence I'll talk about doesn't come out of nowhere. It actually is fairly well understood in the context of Hermitian matrix model. This is what Bouchard and Ena explained in that paper from many years ago. Okay, but now we want to get away from matrix model, so we'll forget about matrix model. And I'm just going to state what this statement is, what the correspondence is, and what is known, and what are the implications of this statement. Okay, and the idea that you should keep in mind is we're trying to use topological recursion to quantize the spectral curve. Okay, so let's start with a spectral curve. So again, we start with a spectral curve, but now I'm going to focus on a special type of spectral curve for this presentation, even though it can be generalized. So we'll take spectral curve that is constructed out of an algebraic curve. So what do I mean here? So you start with the polynomial equation. So C here is the zero locus of a polynomial equation in two variables. I'm going to take these variables to be just C variable. You can do it as C star too, but I'll focus on this case for the presentation here. And then you parameterize that curve, that complex curve. So you get x as a function of a parameter and y as a function of a parameter. And that basically constructs x and omega 0, 1, and the Riemann surface being the normalization of the spectral curve of the algebraic curve here. And then you take omega 0, 2 to be the Bergman kernel. So that's the way you would construct a spectral curve out of these algebraic curves. And I'll call these spectral curve algebraic, just so I don't have to repeat all the time, constructed from an algebraic curve. So I just mean that basically there is a polynomial curve under the hood. Okay, so now let me define the object that I call the wave functions. I've mentioned that before. There's a new object, which will be the wave function, which comes in matrix models from expectation value of determinant. So the way it's constructed is as follows. So you pick a system of correlators on your spectral curve. Now suppose that it satisfies TR. Well, you could construct the wave function for any system of correlators, but that's the case that will be relevant. So you define the wave function as being an object, which I'm going to call psi. It's a function of a single parameter, z. And the formula looks similar to the partition function of various structures, but it is different. So the sum here is over the same type thing, same h bar and factorial. But here I get some integrals of the correlators. Well, let me not write the variables. And I have to be careful with the 0, 2. Okay, so now this one thing I should mention is that here this sums over all G and N, so not just the stable one, so it includes 0, 2 and 0, 1 in the sum here. And for the 0, 2 case, you have to be a little careful. You need to remove the double pole. And the way you do it is like this, where x is the x of your spectral curve. Okay, and this is this formula is the one that comes from the relation between the determinant and the exponential of the trace of the log. So in matrix model, as I've said, the product of traces essentially are generated by these correlators. This is essentially the determinant, and through that formula from the previous slide, in matrix models, you get a construction that looks like this for the wave function. Okay, but now we can do that in general. We just state or construct that object for any system of correlators that satisfy topological recursion. Now, a few things you should note here is that the integral here, all the variables are the same. So omega gn is a differential form in n variable, but you integrate and all from the same z here. So it's like a specialization, right? You get only one variable left, right? So you're losing information when you construct the wave function. And there's an alpha here, which I did not specify what it is. This is a choice of base point for your integrals. In fact, you could do things a little more generally here by choosing a divisor, but does not really matter. And of course, the wave function depends on this choice of base point because it will change the integrals here. So usually you want to take it to be a pole of x, but it can be generalized. But usually you take alpha to be a pole of x, so a puncture of your spectral curve. And you integrate, and psi here should have a dependence on alpha. I'm just not writing it for simplicity, but it depends on the choice of alpha. Okay, so that's what's called a wave function in the theory of topological recursion. Now, how does that appear? So, okay, so what we want to do is quantize the spectral curve. Or we want to see topological recursion as a way of quantizing the spectral curve. So what does it mean? So spectral curve here is algebraic, so it's a zero locus of a polynomial equation. The idea of quantizing here is to think of x and y as being non-commutative operators. So you take of y as the momentum, x as the position. So you do a standard quantization where you replace these commuting variables by non-commuting, anti-commuting, well, not, well, commutator is h bar here. So you replace your y by h bar ddx and x by just multiplication by x, the operator that multiplies by x. So standard quantization that you would do in quantum mechanics. But of course, this is not unique, right? So if you take a curve and you quantize it, there's no unique way of doing it in general, right? Let me give you an example. If you start with this curve, xy squared minus 1 equals to 0, this is actually the Bessel curve. It's an example that we've seen a lot. It's basically the Bessel curve. Now, if you quantize it, then you want to replace x and y by operators, but they don't commute. So you can, if you think of that as xy squared minus 1 in the way I wrote it, and just replace directly x by multiplication by x and y by h bar ddx, you'll get this particular operator, x d 2dx squared minus 1 as the quantization of the curve. But you could have written the curve like this, right? This is the same curve because x and y commute, but now that would give a different quantization. That would be this, which, okay, you can commute things and you can rewrite it like this. Commute ddx with x, so you'll get plus h bar minus h bar ddx. Minus 1. Right, which of course the two are different operators, right? There's a correction. So there's no unique way of quantizing by this procedure. So when we say that topological recursion quantizes the spectral curve, so the idea is that there will be a quantization that that is determined by topological recursion. Okay, but the idea to define quantum curve is to define basically quantizations of spectral curve, generally speaking, so including potential corrections that arise from choices of ordering and things like that. Okay, so this is what we call a quantum curve. A quantum curve is a quantization, so let me write p hat, is a quantization of the spectral curve, the algebraic spectral curve. Okay, but what do we mean by that? So what we mean is that it is an order D. So here I'm going to take C to be degree D in Y. So when you replace Y by derivatives, you get an order D differential, linear differential operator in the variable X, such that, I guess after normal ordering, I should specify that, it takes the following form. It takes the form Okay, so what does it look like? So p hat here is going to be an operator, so it's a function of x, h bar ddx, and potentially extra h bar dependence. You want the leading term to be just the polynomial that you start with, normal ordered. So this would be this thing here, right? Everything is normal ordered, so all the derivatives on the right. So that's the leading term, but then you can get corrections. In fact, in principle, you get an infinite set of corrections, but we usually want to get only finitely many. Where these corrections, these Pn are now new things. They could be anything, generally speaking, but they're degree less than d, so less than the degree of the original polynomial. And you want to have only finitely many non-vanishing ones. Right, otherwise, well, I mean, you could study quantum curves with infinite corrections here, infinite set of corrections, but we don't usually want to do that. Okay, so this is kind of a generalization here, but you see this is exactly what happens if you change the ordering. You're going to ask me every hour. So this is what happens if you change the ordering. If you look at the second example here, so the first term is the same. The first term minus 1 is the same. So this is the leading polynomial in normal order. And then you get a correction with an h bar in front, right? So this is a polynomial in h bar ddx and x, but with an extra h bar in front. So that's a correction. So this is a more general statement where we also allowed corrections that don't necessarily come from choices of ordering, but that would be a general definition of a quantum curve. That's what we mean by quantizing the spectral curve. Okay. How does TR produce such a quantization? What is the statement? Okay, well, the statement, which is a claim for now, and let me call that the topological recursion quantum curve correspondence. So this is my own way of calling it. This is not like it's not like the ADS-CFT correspondence that everyone calls ADS-CFT. This is just my way of stating it. So don't search for topological recursion quantum curve correspondence. You probably won't see many papers, but there's a lot of papers on quantum curves. So what is the statement here? So let me start again with an algebraic spectral curve. And construct the wave function. Okay, so what do I mean? So you first construct the correlators using TR, and then you package them together in this big object that I defined a few slides ago. So construct the wave function. Let me write to be explicit from topological recursion. Then the statement is, and that's a big statement, is that there exists a quantization, so a quantum curve, p hat, such that it kills the wave function. That's the state. Now, I should qualify a little bit. So, well, I will have to qualify in many ways. But let me first just explain the statement. So psi is a function. The way I've defined psi 2 slides ago, it was a function of z, right? Because z would be the parameter you use when you parameterize your curve here. While the differential operator that I define as quantum curves is a derivative in x. But of course, x is a function of z. So you can rewrite this if you want as everything in terms of z. And that's the statement here. So one way to think of that statement is that you rethink p hat as a differential operators in z, not x. Another way of thinking about it is that this is an x, but then you take the wave function and you expand in x or 1 over x. But either way, this would be a statement. The easiest way to think about it is just write everything in terms of z. And that's so as living on the Riemann surface. Oh. Okay. So that's the topological recursion correspondence. And there's a few remarks here that I should do. First is that when I constructed psi, I told you that it depends on a choice of base point. So if you change the base point, you change psi, you change the wave function. So in particular, changing the base point should change the quantization. And indeed, that's what happens. Should change the quantum curve. So the actual precise statement here is that for a choice of wave function, so a choice of base point, there exists a quantization. And that's certainly not expected to be true for any random choice of base point. But it should be true for when your base point is a pole of X. That's the idea. As long as the correlators don't have poles there, so that is not a ramification point that contributes to TR. Otherwise, the integrals wouldn't make sense. So that's the usual statement here. But it can be more general than that. So there's other choices of alpha of base points where you still have a quantum curve. Okay, so that's the first thing. Second thing, which is important, is as stated, my correspondence here should only hold for genus 0 spectral curve. But this is not because it shouldn't hold in general, it's because I should change the way it's stated. So for g greater than 0, you need what's called a non-perturbative wave function. So basically, you need to replace the expression that I wrote for the wave function by a much more complicated looking expression, but still determined in terms of the correlators. And this was studied first by Enar Marinho, and then many other papers, but including a more recent one by Enar, Garcia-Falde, Marshall, and Orante. But this is well known. So the non-perturbative wave function is well known what it is. I just don't want to write it down. So that's just for simplicity. Another thing I should say is that I've defined things here in terms of a quantization of the spectral curve. That's very nice and easy to see. But from the point of view of integrability, the more natural thing to do would be to look at a system of first order equations instead of a degree D, order D differential equations. That would be more natural. But again, this is not a big deal for now. Just a statement if you look at the literature. Okay, but the upshot of this statement is that, and this is the kind of precise way that topological recursion constructs a quantization of the spectral curve. The more precise statement is that topological recursion reconstructs the WKB asymptotic expansion or asymptotic solution to a quantum curve. Right? If you remember your WKB analysis, WKB is basically solving. So you have if you have an equation like this one, for example, Schrodinger type equations where there's an h bar coming with a dx, then the WKB solution would be find solutions that are asymptotic solutions in h bar that starts with exponential of 1 over h bar times something, which is exactly what the wave function is. The wave function, if you look at this, it starts with 2g minus 2. So g equals to 0 and n equals to 1. So that starts like h bar to the minus 1. So 1 over h bar. The 1 over h bar term is just the omega 0, 1, which indeed omega 0, 1 is just y dx. So if you calculate it quickly, you'll see that basically the semi-classical limit, so the leading term of your asymptotic solution does indeed always give you this first term here for the quantum curve. Okay, so if you keep only the 1 over h bar term in your wave function, it is always annihilated by this. But the statement here is that it's not just the 1 over h bar term that you get from omega 0, 1. The correlators give you the full asymptotic series, the full WKB series. So that's a very powerful statement. Okay, so again, that's a good exercise. If you want, you can just look at omega 0, 1. You can check that indeed you're going to recover. If you act any quantum curve to first order, you're going to recover the original spectral curve that you start with. So that's exactly what you want as a semi-classical analysis. Okay, so that's a very powerful statement. And it turns out to be very interesting in lots of different contexts, as was the case before for the relation between expansions at different points. This quantum curve statement is also has nice consequences. So first, let me tell you what is known about the statement. So okay, so I should say this claim, this correspondence, as I said, dates back from 2006 in Berger and Enar, but it became much more well-known quite a few years later. There's been some paper of Glukov and Sulkowski, for example, where they studied that in the context of knot theory, and that became very much more explicit way of stating it for general topological recursion. And since then, there's been a lot of papers that prove this construction, this statement for a very special case. For example, you take Hurwitz. Well, Hurwitz numbers don't fall in what I'm talking about here because it's not an algebraic curve, but this statement also is expected to hold for non-algebraic curves like the Hurwitz spectral curve. But for example, you could take Hurwitz numbers and then try to prove this. You could take R-spin Hurwitz numbers, try to prove it. You could take covariant theory of C3 and try to prove it, and so on and so forth. And there's been a lot of papers doing that. So there's at least 40 papers probably out there that do it case by case with different contexts. And usually what people use is some knowledge of the enumerative geometric problem, for example, Hurwitz numbers or whatever. You have some sort of other ways of thinking of these numbers, and then you can use these properties to show that there is a differential operators that kill the wave function and that this differential operator is a quantization of the original spectrum. In fact, that's another way that might answer also one question before. How do you get the quantum curve? How do you get the spectral curve? Well, if you know a quantum curve, then you can get the spectral curve easily because you just take, if you know that your problem is killed by a differential operator, your enumerative geometric problem, then you get the spectral curve directly just by taking the classical limit of the quantum operator. But usually you don't know that. Okay, so it's been proved in a lot of different contexts, but I would say probably the first result that was just proving this statement directly from the properties of topological recursion without referring to a particular enumerative geometric problem where you have more knowledge of the wave function was a paper of Bertrand and myself. And what we prove in that paper is that this holds for a large class. So it's a fairly large class. It's determined by a condition on the Newton polynomial that there is no interior point, but it's a large class of algebraic genus 0 spectral curve. It's a large class, but it's genus 0. So many problems, I mean, so far, all the problems all the examples I gave you were always genus 0 spectral curve, but there's a lot of interesting problems that are not genus 0, like going to the theory of local P2 that we talked about. However, one thing that was nice in this result is that we worked with spectral curve with arbitrary ramification. So we did not impose simple ramification. So that's kind of general in that sense. But much more recently, 2 years ago, I think there was a paper that I've mentioned before, Elba Garcia-Falde, Bertrand Hénard, Olivier Marchal, and Nicolas Armentin. And they prove in a much more general statement that it holds for all algebraic curve. And again, they prove it just using properties of topological recursion, so that there's no other knowledge needed. So any genus. However, they impose only simple ramification points. But it is expected that this is just a technical reason. They impose that so that formulas are manageable. But it's expected to hold, based on their work, it's expected to hold for all algebraic, which would be very cool. So that's the state of the art here. So now proving that for all algebraic curves based on their work is something that should be done. Someone has to do it. Someone brave enough should do that. But I don't see why it wouldn't work, because that going from genus 0 to higher genus was difficult because you have to work with this non-perturbative wave function, but they've done that. So now I think that should work. Now, as I said, there's many generalizations because you can go to non-algebraic spectral curve, right? You can basically look at curves that don't come from polynomial curves. So one example was the Hurwitz curve. The Hurwitz curve, basically, you can rewrite as this curve if you think of it as x and y. So it's not a polynomial in x and y, right? It has an exponential here. So you can ask the same thing. Is there a quantization that kills the wave function? It's still expected to hold for non-algebraic spectral curve. And in fact, in that case, it's proven, for example. So there are many cases here where it's proven. So most cases of Hurwitz numbers, or maybe all of them, it's proven. Grommelton theory of P1 is proven. All the Grommelton theory of toric free-fall where the mirror curve is genus 0. So C3 resolve kind of fold. all these cases are proven case by case that indeed there's a quantum curve that kills the wave function. But what's interesting is that in all these cases, the way it's proven is using knowledge of the enumerative geometric problems, so using fermionic representations or stuff like this, or topological vertex, or some stuff like this to prove the statement. No one knows how to generalize these two theorems, where the idea is just to start with topological recursion or loop equations, if you want, and repackage them, basically show that the wave function is killed by quantization directly. No one knows how to do that for non-algebraic spectral curve at this stage. But, and that's a very interesting question. I don't know how to do it. I've tried a bunch of things, but unsuccessfully so far. So it's not clear how to do that systematically for non-algebraic spectrum. Now, I hope that what I'm saying is right, that it is still not known, because maybe there's been some more recent papers I'm not aware of. But as far as I know, this is the state of the situation. Now, one thing that is cool here, as I've said, is when you have a result, this is not an application, this is purely formal. But all we're doing here is just studying topological recursion for its own sake and asking whether it provides a quantization of the spectral curve. But now you can see in different contexts, what does that mean, right? So in the context of Hertz theory, Groverton theory, it gives you this nice statement that, if you package the Hertz numbers of Groverton invariance and this object called the wave function, then it's killed by a differential operator. It's a very nice, non-trivial statement. In the context of knot theory, so this is something I talked about in the question at the end of the first hour. So in the context of knot theory, this statement should be precisely a very well-known conjecture, which is called the AJ conjecture, which I think is still a conjecture in knot theory, if I'm not mistaken. But AJ conjecture is basically exactly this quantum curve correspondence, topological recursion quantum curve correspondence, if topological recursion works for knot theory, which is still conjectural. But the AJ conjecture is basically very similar. So you start with the A polynomial, and the statement here is that there is a quantization of the A polynomial that kills the Jones polynomial. And topological recursion here in this context should be the statement that if you take your A polynomial and think of it as a spectral curve, and the correlator, you construct the correlators using TR and construct the wave function, that should give you the Jones polynomial. So in other words, this corresponds, if we could prove that, well, there's lots of things to prove here. But if we could prove that first, what I just said is true, and also that the topological recursion quantum curve correspondence holds for these curves, because these are not algebraic, even though they're polynomial, they're actually in C star. So the variables you can think of e to the x and e to the y, not x and y. So it doesn't fall into these classes. But anyway, if we could make progress in these directions, maybe we can provide a completely different point of view on the AJ conjecture. I mean, we have a different point of view, but different proof, the AJ conjecture, but that's completely conjectural. But the AJ conjecture is a very well-known conjecture in knot theory, and you see that this comes naturally just from the formal statement I talked about. Okay, so that's kind of cool, and as I said, and the other area of interpretation, then this has different conjectures, different names, but from our point of view, it's just a formal conjecture. Great. So, and one thing that is very interesting too is to go beyond asymptotics. So what I've just argued here is that topological recursion is a way of reconstructing the WKB analysis, or the WKB asymptotic solution for a quantum curve. And that's the statement. But of course, as has become very popular in recent years, the question is, can we go beyond asymptotics? Forget the go. Can we go beyond asymptotics? So there's been a lot of works. For example, Marcos Marinho and collaborators have published many papers over the years studying this question, in not in the context of topological recursion, but for example, context of topological string theory, matrix models, many Pain-Levé equations, all these different contexts where they start with WKB, but they do a Borel summation and they study resurgence and all these different things. So we can ask the same thing here. So can we resum a solution? I put that in quote, but what I mean is that we resum it in a well-defined way to reconstruct out of the perturbative solution the actual non-perturbative solutions of the quantum curve. Right, so there's many ways of doing that, but there's some well-known way. Borel summation is one of them, and there's a whole study of resurgence, trans-series, all these different things here. So that's a very natural question, and the question is, what does TR have to say about this? And this is something that hasn't been studied at all. I think it is a very interesting area to research on, but it's very new. So far, TR has always been used to reconstruct, basically perturbatively. But can we get more information? And in particular, you could ask, okay, does TR always produce asymptotic solutions that are Borel resummable, right? So there's some properties. I'm not an expert at all on this. So asymptotic solutions, not an expert at all on this, but there's some conditions on, they shouldn't diverge too quickly. I mean, there's some conditions here on the asymptotic solutions that are needed so that you can resum them using Borel resummation. Well, one can ask, if you construct your wave function using topological recursion, is it always Borel resummable? That's, again, completely formal statement. You can, in principle, probably answer that just from the structure of topological recursion. And if you can, again, now you look at all the applications, all the different contexts, and that would give you some very, very powerful statement in all these different contexts. And this has been studied very recently. So I think there's a paper that was published a few months ago, I think in September maybe or something. I think it's Boro and R and Giacchetto. But if I'm not mistaken, where they ask this question and provide an answer, or at least a partial answer. I'm not too familiar with the paper, so I'm not going to say more about this. But yeah, but I think that's an area that probably there will be quite a bit of developments in future years, because that sounds very exciting. And you can ask a similar question: can you get large genus asymptotics from topological recursion, right? If you have an asymptotic solutions, you can look at what happens for large genus. And then does TR have anything to say about that? Again, there was a paper very recently that studied large genus asymptotics of intersection numbers and so on using this approach. That's gives a nice result. So yeah, so anyway, I guess I won't say too much more about this because it would take too long. But I think the moral, what I want to end with maybe is the following. Maybe that's what you should take out of these lectures, is that it's basically, let me write it as follows. Okay. Is the power of abstraction. So what do I mean here? Well, so this lecture was quite abstract. We studied the formalism of topological recursion in connection with area structures, loop equations. Then we talked about using the statement that the correlators are globally defined on the spectral curve to get nice results in enumerative geometry. Now we talked about how TR provides a quantization of the spectral curve and all of that. But all of this was completely formal, right? But anything you can prove formally about the structure becomes very, very powerful, because we already know, so everything you can prove formally about the structure of TR is very powerful, because we already know that TR appears in many, many different contexts. So if you can prove something formally about the structure of TR, leads to lots of, let's say potentially, because you don't know, but potentially interesting results in all kinds of different contexts. I mean, think of what I just talked about Borel resummation. If you can prove that you get, asymptotic series that are Borel summable, say, then you know it's Borel summable everything that is calculated by TR. I mean, that's a pretty big statement, right? So usually you would just prove it case by case, but now you would just, big sweep, just prove it all at once. So that's the idea here. So I think that's kind of a cool, like symplectic invariance is another example. All these different properties that are completely formal lead to lots of interesting consequences. So yeah, so maybe I'll end with that because that's a good place to end. I wish I could say more about connections and applications, but that would be for a completely different lecture series. So maybe another time. Thank you very much.